Hello and happy Tuesday. That's right, you should be viewing this video on Tuesday, April 14th. And today we're going to be going over 3 math problems from section 11.1. So let's get started. You need your textbook to follow along, and we're going to start on page 297. So page 297. Okay, if you need a moment to pause the video and find it in your textbook, that's cool. But go ahead and find that. Again, we're going to be on page 297. We're going to do that big example problem. And please write down these problems as we're going over them. And so you can actually add them to your notes from 11.1. You can start a fresh sheet of paper. That's fine too. Have a calculator handy so you can work out the problems along with us. And you'll be asked to submit a form after you watch this video. So be prepared for that as well. So again, be on page 297, have your calculator ready, follow along, and here we go. So page 297, the problem says that you lift a 7.30 kilogram bowling ball from the storage rack and hold it up to your shoulder. And I hope you like bowling. I hate bowling, but for whatever reason, you're in a bowling alley and you're about to bowl. So you get the ball and you take it off the rack and you move it up to your shoulder. And they go on to give you the heights for both. And so if you look at the diagram, it's actually really helpful to picture it like this. From the floor to the rack is one distance, and that is 0.610 meters. And then if you go all the way up to your shoulder, that's a different height, which is 1.12 meters. And so you need to make a note of that. And I just noted that by doing H1, and I put the initial 1, and notice that, oh, you know what I didn't do is put my 0 on the end. That's bad. Let me change that. Because it's significant digits, I don't want to get messed up later on. Okay, so the original height, or the height up to the rack from the floor is here. And then the height all the way to your shoulder is here. And notice that those are in meters. That's appropriate. Notice they also gave the mass of the bowling ball. It's in kilograms. And that's good, because if it were in grams, we would have to change it over to kilograms. Remember, we want all of our units to match the units that are in a joule, which is kilogram times meter squared per second squared. So that's important. All right, so there are actually 3 little questions with that. So when I said we were going to do 3 problems, we're actually going to do 5 problems because this one has 3 parts. Sorry about that, but you're used to that by now. So A says, when the bowling ball is at your shoulder, what is the ball Earth system's gravitational potential energy relative to the floor? That's just a fancy way of saying what is the gravitational potential energy at the height of your shoulder in reference to the floor. And so we need to use a formula for gravitational potential energy. Yesterday when we were doing the video, I actually gave you 2 formulas. One of them was based on the weight of the object, and it was F sub g times h. And then the other one, the first one, was based on the mass. That's the one we need to go with because we were given the mass of the bowling ball, not the weight. And so you would choose the fact that gravitational potential energy equals mgh. That's what you would do. Okay, so we need to just plug in at this point. Okay, so I'm going to use 7.30 for my kilograms. Okay, and then for acceleration due to gravity, we're going to say that we're on Earth for all of these problems. So we're going to use the 9.8 meters per second squared as standard for little g. And then I need to do the height. Make sure you grab the height that was from the shoulder all the way to the floor, or vice versa, not the rack. So we're going to use that 1.12 meters. And then it just becomes a matter of multiplying these together. So go ahead and do that in your calculator. If you need more time, you can pause the video, obviously. Okay, but when I did it, I came up with, before rounding for significant digits, I came up with 80.1248. And it's the type of energy, so it's going to be in joules. Okay, and of course we need to round. And it's funny because I went back and put that 0 on the 0.61, but because of the 9.8, we can only have 2 significant digits. So it's going to round to 80, but I need to note that that 0 is indeed significant. So there are a few ways I could do that. One of the easiest ways is to put a line over the 0. Okay. I could also, instead of doing the line, I could add a decimal point, or I could do 8.0 times 10 to the first. Nobody's going to do that, but you could do that if you wanted it. There you go. Okay, so that was A. Okay, and let's move on. We're still on that same example problem on page 297. Let's look at B though. So I'm gonna go to a different dry erase board because this one's getting it's running out of space. So let's look at B. It says when the bowling ball is at your shoulder, what is the ball earth system's gravitational potential energy relative to the rack? So in other words, when you're holding that ball at your shoulder, okay, what is the gravitational potential energy if you're just comparing it to the rack? So now our rack would be 0, like a reference level of 0. And so we're going to have to figure out the height the height difference basically. And so if we were all the way up at our shoulder, okay, we would have the ball at 1.12 meters above the ground, but the height of the rack itself is 0.610 meters. And so I'm going to find that difference, which is 0.51 meters. So that's the difference. Okay, I should have really done this as delta H instead of H, but that's okay. So now when I do my gravitational potential energy, I'm still going to use the same mass, still going to use the 9.8 meters per second square for acceleration due to gravity. But for my H, I'm going to use this 0.51 meters. Now, you don't have to do this as a separate problem. You could just do like the M, the G, and then you could do parentheses, this minus this, and that would be like all one thing. That's totally fine as well. It's actually a little bit shorter to do that. But since I already did the math, I'm going to proceed on as I have it. So we're going to do it 7.30 kilograms. Okay, and then we're still using 9.8 meters per second squared for the G. And then my height in this case is only 0.51 meters. And so make sure if you need to pause the video, you can do that. But go ahead and run this in your calculator and see if you got the same thing as me. I get 36.4854 joules without rounding. And then again, because of that 9.8, we're only going to be able to do 2 significant digits. So it's going to be 36 joules. And then finally, C. So we're still on the example problem. We're doing C now. It says how much work was done by gravity as you lifted the ball from the rack to the shoulder level. And so we did the work energy theorem where work was related to change in kinetic energy. Well, work is also related to change in gravitational potential energy in our case. So that's nice, isn't it? So in this case, we can just do the, actually, it's like the basic thing that we already did. Like it's the same thing as the last problem because our change in height was the 1.12 meters minus the 0.61 meters. So it's basically the same exact thing, except I would probably I'll go ahead and write it out as a formula. So it would be mg delta H. So I'm going to go ahead and do my 7.30 kilograms and then the 9.8 meters per second squared. Oh, I'm going to run out of room. Okay, but I would do like this right here down here. So I'm not going to write the units because I'm going to run out of room. But basically it's what we just did. And so it's showing how the change in gravitational energy is related to work. So we had to do that much work on an object to lift it from the rack to our shoulder height. And remember, work is a force moving an object through a distance. Like in the past, when we had done work problems, it was all like linear. And so we were like pushing a sofa, or we were pushing a box, or we were pushing a kid in a wagon, or pulling a kid in a wagon. And so it was all linear. And now when we're talking about gravitational potential energy and it's all due to height, we're just changing that distance to a height. And then force is basically the weight of the object that you're going to have to lift. And so think of it in those terms, and it'll really help you adapt to material in this chapter. All right, so that was our first problem, which is actually 3 problems. Sorry about that. Okay, the next one, sorry, had to grab this off the ground. The next one we're going to do is on page 298. Okay, so go ahead and flip over the page. On page 298, you'll see some practice problems at the top. And we're not going to do all of these. We only have 2 more. So we're going to start off with number 6. So find page 298, number 6. And I'm going to go ahead and read that. If you slowly lower a 20.0 kilogram bag of sand 1.20 meters from the trunk of a car to the driveway, how much work do you do? And so just kind of visualize taking a bag of sand and you're taking it out of the trunk of a car and you're lowering it straight down. For these purposes of this problem, it's like straight line motion here. You're just lowering it straight down onto your driveway. And so let's write down what we're given in the problem. Okay, we know, actually I already wrote this part down to speed things up. Okay, but we know that the mass is 20.0 kilograms. Again, don't be a slacker and leave that part off. The height is 1.20 meters. And I'm going to say that up is positive in this problem. So if I'm lowering it, I'm going to actually, you know what? I'm not going to worry about positives and negatives. It's okay. We're just not going to worry about that right now, because I want to keep things as simple as possible. So anyway, we're just going to say that the height is 1.20 meters, and we're trying to figure out how much work is done. Now, normally, remember, work is force times distance. Okay, but we're also going to figure that the force is going to be the same thing, or let me back up. The work is going to be the same thing as delta GPE. So let's go back to that work energy theorem. And so we're going to say that work is the same as delta GPE, or in other words, the change in gravitational potential energy. So let's break that down. So delta GPE would be equal to the mass. The mass isn't what changes. Like the sand still has the same mass no matter what. And then G isn't going to change, the acceleration due to gravity. What changes is the height. So we're going to go ahead and do the mass as 20.0 kilograms. And then the G is going to be 9.8 meters per second squared. And then for the delta H, okay, we're going to do basically 1.20 minus 0, which is basically 1.20. And then it becomes a matter of multiplying it through. So multiply that all through. If you need to pause, that's cool. But I'm getting 235.2 joules. And because of the 9.8 again, we can only have 2 significant digits. So of course this would round to 240 joules. Okay, so there you go. Check your work. All good. Okay, and then one more. We're going to do the one right below that, number 7. So let's look at number 7. It says a boy lifts a 2.2 kilogram book from his desk, which is 0.80 meters high, to a bookshelf that is 2.10 meters high. What is the potential energy of the book Earth system relative to the desk when the book is on the shelf? And so basically, if you move the book from the desk to the shelf, what's the gravitational potential energy? And so we have the mass in kilograms. That's awesome. The original height of the desk was 0.80 meters. And then the bookshelf, I just put shelf, is 2.10 meters above the floor. So we're going to have to do the same basic thing that gravitational potential energy. Okay, since we're doing it from only the shelf to the top of the desk, we're still going to have to do that delta H. So that's going to be mg delta H. So I'm going to use the 2.2 kilograms for the mass. G is still 9.8 meters per second squared. So you can see what I'm doing there. And then I need to do my delta H. And so it went all the way up to the bookshelf. So I'm going to do that one first. That's my final. So 2.10 meters minus where it started. It didn't start at 0 this time. It started at the desk, which was 0.80 meters. So my equation should look like that. And then again, you're going to use parentheses in your calculator when you do this part, which I'm sure you already know that. But when you multiply this through before rounding, I get 28.028 joules, which when you round for just 2 significant digits, 28 joules. There you go. All right, so we didn't do any problems that had the weight given instead of the mass, but if you should run across something where the weight is given instead of the mass, the weight would be in newtons, and you would just simply leave off the G because the weight is already taking into account that G. So it's even simpler because you just only use the weight times H or delta H, and then you'll get the correct answer. So go ahead and respond to this video on the form provided, and I'll see you guys again next time.